Dear all, I am Manjunath, TG, Associate Professor from Sai Vidya Institute of Technology, Bangalore. In the last few sessions, we discussed about the signal flow graph and other related problems. Now let us start a new model, that is time response analysis of control system. So in this model, we will be discussing about the first order system, then second order system, then related problems and its analysis, and also error constants. So these are the topics which we are going to discuss in this model. Now, why this time response analysis is very important in any control system? So in our general daily life, we want everyone to respond very quickly. That means time management is very important in our life. So hence the time response is also very important in any control system. So what is response? Response means output. So response means output. In any system, we are expecting some output for a given input. We don't want this system to respond or to take more time to respond. We want every system to respond very quickly. Quick means time taken to respond, the system must be less. Means it should not take more time. Hence, so time management in the system is very important. Hence, the necessity comes to study the time response analysis. So response, we are analyzing the response, nothing but output, with respect to time or as a function of time for a given input. That is the time response analysis. So why we need to study this and what is time response analysis? What is time response analysis? Analysis of a response, nothing but output, as a function of time for a given input is called time response analysis. Now, why we need to study this time response analysis? In most of the practical systems, the actual input signal is not known. In most of the practical systems, actual input signal is not known. Then what we will do, we will take the characteristics of actual input signal and we apply those signals to determine the performance of the system. Now, what are the characteristics of the actual input signal? It is sudden shock, sudden change, then constant velocity, constant acceleration. Now, by taking the characteristics of these input signals or these, we are going to apply some test signals. So, what are the test signals we are going to consider? We are going to consider the test signals like impulse signal, then a step signal, then a ramp signal, then a parabolic signal. So by taking these as standard test signals, we apply the inputs to the system to determine the performance of the system. Now, the question is, why we are doing this analysis? Now, let us take a simple example to make you to understand better about time response analysis. Suppose if I consider car. If I start a car or if I start the ignition of the car, immediately you might have heard a loud noise or a sound. Then after some time, the higher sound disappears, but it settles to a lower level and then it becomes constant. That means if I start the car, immediately the loud noise. So if I represent that in a graph, if I represent that noise as a graph, so at t equal to 0, I am going to start the car. Immediately there is a loud noise, then that noise slowly decreases and then it settles to a minimum sound or a noise. Later the higher noise disappears. That means after the application of the input means ignition, the car responds like this. Now here to settle to the final value or the final level of noise, it is taking some time. That time we call it as transient time in control system. Then after it settles to a final value, the remaining time we call it as steady state time. So if you observe this, you are getting two responses for a given input. This response we call it as the transient response. So this portion of the response we call it as a transient response, and this portion we call it as steady state response. So we have two responses now. Let us write two responses. That is total response is equal to, so transient response plus transient response plus transient response plus steady state response. So it is taking, the system is taking, or the system, nothing but car here, is taking some time to respond to the input. So that time is called transient time. Then after settling to the final value, the remaining time we call it as steady state time. So this is the total response for a given input, and this first portion of the response is called transient response, and the second portion is called steady state response. Hence total response is equal to transient response plus steady state response. Okay, now let us define what is a transient response and steady state response. Transient response is defined as, it is the portion of total response. It is a portion of total response during which the output changes from initial value to the final value. So transient response, it may be defined as, it is the portion of the total response during which the output changes from initial value to the final steady state value. And the time taken to change from initial value to the final steady state value is known as transient time. And what is steady state response? It is again the portion of the total response during which output is constant, and it is steady, and that time, corresponding time, is called steady state time. So here this is not a good designed car. So we don't want this delay. So we may expect the car to respond quickly. In some cases, the response may be like this. So when you apply the ignition or when you start the car, then it may go like this and it may become steady. That means it takes less time. So in transient analysis, we need to minimize this time. We need to minimize the time. Why we are going to do transient analysis? In this analysis, our intention is to minimize the transient time. Means we have to design a system in such that it should respond very quickly after the application of input. In steady state analysis, we are going to analyze for the error, whether it has reached the steady state value properly according to what we are expecting, or if there is any error. So we are going to minimize that error in steady state analysis. Now let us take another example to make you to understand the time response analysis in a better way. Now let us consider another example where electrical system is considered. Let us measure the current taken by the circuit. We have connected an ammeter. When you switch on, assume that there is a switch here. When you switch on this, immediately current flows. The ammeter would show reading. So this ammeter should respond very quickly in this case. But what happens if it is a analog meter? It rises to some level and it becomes constant. Assume that you are using here 10 volts and R is equal to say 2 ampere. So then current becomes 5 ampere. So it has to reach 5 ampere. But to reach to the final value or to the pointer deflection, it shows it deflects to 5 ampere. To deflect to the final value, it takes some time. That time is called transient time. Then it settles to the final value, and that is called steady state time. But here, in this case, so to settle to the final value, it is taking some time. That time need to be minimized. So hence, in transient analysis, our intention is to minimize the transient time. So once it settles to the final steady state value, so whether it is exactly 5 ampere or if there is any error, so this error we need to minimize in steady state analysis. That's why, so any system we take, so our intention is make the system to respond very quickly after the application of input. Hence the time response analysis study in control system is very, very important to design an efficient and a stable system. Now let us conclude why we are going to study this time response analysis is to improve the stability of the system. To improve the stability of the system, then to improve the accuracy of the system, and to minimize the error in the system. That's why we need to study this time response analysis. So let us discuss the next session, the very important thing, that is standard test signals that are applied to a control system to determine the performance of the system. Thank you for watching.